out there? Welcome back again. We are still on revising. We're looking at correlation and regression, okay, to answer some of the questions. Okay, so let's see what we have in our next question. So our next question here, very important to read. Read, read, read. It's pointless to answer the question because you might be answering something wrong, okay? The times achieved, those are the times achieved by winners of men's 100-meter swimming events at the Olympics game from 1972 to 2004 can be accessed from this website, okay? So the scatter plot was shown, okay? So here we have data from 1972 to 2004, but this was men's Olympics, swimming, the times they finish, okay? For what? What event? Are we given an event? A 100-meter event. Are we together? Let's see what we have now. So the 100-meter event. So there's a scatter plot. Those are the times for men. So there's a scatter plot. You can see that in 1972. So the times, I mean, this is around 50. We can see there, I think it's around 50-something seconds, you can see, in 1972. 1976, it's 50. Can you see 1972? We're getting 50 seconds. So I read my questions. We have men's Olympics from 1972 to 2004, 100-meter event times. Okay. What do we have to answer now? Or read some more. Let's see. Okay. Indicate whether a linear or quadratic or exponential function best fits the data. So the scatter plot of times taken by winners for men for 100-meter at Olympics. Okay. So looking at this, is this linear, quadratic, or exponential? What will you go with? Linear. Why linear? Quadratic or exponential? I will go with a linear relationship. I think this is a linear relationship because the data given here follow a linear trend. Okay, I can draw kind of a straight line. If I draw a straight line, the points will kind of be not deviate from the straight line. Not a parabolic. Okay, maybe some might argue and say exponential. Why not exponential? I'll go with a linear because a linear will capture most of the points on our data set. So there's a linear relationship here. Linear. Okay, that's what we'll go with. We together. Okay, good. Let's look at the next question. Now, draw a line of best fit for the data on the graph. So now we have to draw the line of best fit. So just to remind you again that the line of best fit, okay, I kind of drew it. If you look at that, I said, okay, if I draw that this is my line of best fit, but I didn't say this is a line of best fit. I'm explaining where the data follow a linear trend. But when you draw the line of best fit, it's very important to calculate the average for this and the average for that. Because the line of best fit must pass through the mean for that. Are we together? Okay. Let's see that question. So we're talking about the line of best fit. We have to calculate the average times, but the times are there. Can you see? It's not exactly 52 51s. Those are the times. Those are the average times for all those points. Can you see that? If I do that, this is what I get. Okay, this is my line of best fit. My average, somewhere there. So the mean for x and the mean for y. Very important to indicate that point. Okay? You can calculate that point using your calculator. So the average is the mean for x and the mean for y, and the line of best fit is that. Are we together? Okay, that's my line of best fit. Okay. Okay, so here, describe the trends that is observed in these times. Give one reason for this trend, okay? So what is a trend? We can see, what does a trend mean here? We can see that every year, on average, we can see that men's swimming team, they're just getting better and better. They're reducing their time if we compare from 1972, which is actually the highest. And if you look at 2000 to 2004 there, actually, they're taking less time to finish the 100-meter. What could be the reason? Okay? Could have been getting better with time, or also using more technology or training better as swimmers, because they're getting better every year. But also we can see there's kind of an outlier there, something different in 1988. Okay? They could be getting better because of training better. Are we together? As swimmers, this is what is happening. Might be one of the reasons. Okay? Because they're definitely getting better. That's the first. Now, let's see what can be said about the effort of winners in 1976 and 1988. Sure. In 1976 and 1988, what can we say about those two? If you look at those points, so there's a huge deviation from the line of best fit. Are we together? So those two are outliers. Okay? Are we all together? Outliers. So, I mean, according to our regression model, they should be, in 1988, they should be performing there. And 1976, they should be performing there. They're not performing at the best in those 2 years, in 1976 and 1988. Okay? Could have done better. According to our regression line, they are far away from everyone. Are we together? Great, fantastic. Okay, now let's see what we can do here. So, use the line of best fit to predict the winning time in 2008. What is the winning time in 2008? 2008 is somewhere there. So the winning time will be, we have to go on our line and predict. But also looking at 2008, okay, we're kind of extrapolating also. Do you believe that? Is that accurate? Remember, when we interpolate, if we predict within the data, which is somewhere there, the reliability of the answer is really good, but outside, the reliability is not that really strong. Okay? Let's see what is happening in 2008. Actually, in 2008, okay, this is what we get. 47. Okay, that's what we get. It's 47 seconds and 0.21 seconds. Okay, and this is the person actually won. It's Alain Liban, France, in 2008. You can check that. You can, if you have time, try Google that and see that's the actual time in 2008 for the winning person. Okay, fantastic. So now let's look at our summary. We looked at correlation, we looked at the line of best fit, and we looked at linear regression, interpolation, and extrapolation. Okay, very important. Correlation, we're talking about association. Strong correlation, no correlation, or weak or negative correlation or something of that nature. It talks about association between the two variables. The line of best fit is what? It's a line, a straight line, okay, on a scatter plot, but must pass through the mean. That's the line of best fit. And the linear regression is the equation of the line of best fit, which is given by this line, y equals to a, bx. We can do that using our calculator. When does interpolation and extrapolation comes in? When we want to predict. If we predict inside the range, we're interpolating. And the reliability of our forecast to predict, very strong. We can rely on that. But extrapolations outside the data. And, the prediction might not be that accurate, okay? Fantastic, guys. We have come to our end of our lesson. I hope you enjoyed. And we really encourage you to work continuously. And it's okay to struggle with mathematics. It's normal. But to get through that, to fight those challenges, is to work consistency. Consistency is the key. And emphasize again, we don't work just because we have an assessment or test coming. We work even when we're okay. We work even if we understand. Do some problem through previous paper, okay? And seek challenges when there's time, not because you're writing a test next week or tomorrow. We hope to see you soon and keep the good work going.